Okay, so here's what we're going over today, guys. We're going to talk about some of the applications beyond like the different types of corners that we went over, okay, for uniform circular motion. Okay, now this, I mean, we say it like practical applications, but I mean, for you or I, the likelihood of this being a practical solution to a problem for us is unlikely, okay, as the number of astronauts in the world is quite a small number compared to the population of the world, and becoming an astronaut is a very rigorous selection process. Okay? It's not like I go and I get my job interview and the next day I have a job. It's not like that at all. It's like years of qualification and training, and then you can still get washed out near the end. So being selected to be an astronaut is not easy. But one of the applications we're going to be looking at here, okay, is something to do with space travel over, let's say, long periods of time. Okay. This is funny. What's he carrying? On. Usually you spray. Off. Ha ha ha. Very funny. No, it's not funny. Okay. All right. So, one of the big problems with space travel is the effect of weightlessness on the human body. Okay? Right now, we don't have any practical ways that don't involve something being really, really large to generate artificial gravity for astronauts who are going to be in space for long periods. Okay, this isn't like Star Trek or Star Wars where there's just artificial gravity. No one explains how it works. There's just gravity, and everyone sticks to the floor, and it's all hunky dory, and no one cares. Okay, even it seems like when stuff gets shot up completely and should barely be functioning, and there's a total power loss, they still don't seem to lose their artificial gravity somehow. Okay, artificial gravity is not this miracle force field. Okay, we have to generate it. The only way we know how, anyway, is to use centripetal force. We're going to kind of go over how that would work. Sorry, Michael, you had a question? Oh, okay. Yeah, we can use a rotating object to do that. Okay, that's the most realistic and practical way to do that. And in more modern science fiction movies, we do see that a lot more often because, well, people don't just accept that there's artificial gravity anymore. They want an explanation for everything. Okay, they can't just sit down and enjoy a movie. Okay, they have to pick it apart. So anyway, obviously we use that a little bit more. But in terms of a practical sense of actually being able to build that, we're not quite there yet. Okay, so when people are in space right now, they are in zero gravity. This has some very negative effects on the human body because the human body evolved in an area where there was gravity, and actually a lot of our processes depend on that. So one of the things that can happen to you when you go into zero gravity is that your bones and muscles begin to deteriorate. Your muscles atrophy. Okay, that means that because you're not using them to lift your body and move your body around anymore, okay, and they're not bearing the weight of your body all the time, they just get weak. And your body is the ultimate recycler, so your muscle mass shrinks. Okay, so like you have less muscles, your body just recycles the material. Okay, bones are the same way. If your bones are not constantly being stressed, okay, that is holding your weight or being used to walk and lift things and whatever, having weight on them, they will also begin to weaken, okay, because again, your body is the ultimate recycler. And it says, well, we don't need all this stuff tied up in the bones. Let's take it out of the bones and put it somewhere else, or just get rid of it. Okay, and so astronauts tend to lose a lot of their bone density while in space. Okay, in fact, this was one of the things that Chris Hadfield was studying the effects of when he was in outer space. When he came back, his bone density was like that of like a 60, 70-year-old person. Okay, because he just hadn't been exposed to a lot of forces that could make his bones get stronger. Okay, if you have you ever seen people who like break bricks and stuff with their hands and feet? Okay, they don't just walk up and do that day one. Just so you know, okay, it takes a lot of practice and training, and part of that practice and training is actually building up bone density in the part of their body that they're using to break the bricks. Okay, if you compare like bone density scans of someone who does that with a normal person, their bone density is far greater. Okay, because they've constantly created like micro fractures in the bones as a result of the impact, and then the bones heal, okay, and they get thicker and stronger. right? In space, you don't have that, so the bones actually get thinner and weaker. It's almost like having osteoporosis. If you've ever seen like an elderly person, they kind of get hunched and bowed because their bones just get really weak. Pardon me? Kind of, yeah. The more you stress your bones, the stronger they get. Well, yeah, it's not practical to do that though, right? There's that whole like concussion thing, and if you actually did accidentally break someone's bone, you're kind of a long way from a hospital. Yeah. Okay. Now, that's not to say that they're not trying to find ways to, to help with these situations. There's a gym per se on the International Space Station. It doesn't look like a gym on Earth because on Earth we just use weight. We put big heavy chunks of metal onto bars and we lift them and move them around, whatever. Okay. Well, in space, that doesn't work. You could look really cool in space for about a half a second, okay, if you had like a bench and weights, okay, because you could slap like 4 plates on each side and just move that puppy. Okay, like it'd be super easy. The problem would be stopping that puppy. Okay, because Newton's first law would take over. Okay, and off the bench you would go, and you go flying across the compartment, holding on to the weight bar. Okay, kind of hard to stop all that weight once you get it moving when there's no gravity to do it for you. So obviously that's not practical. It's not going to do any good in space to lift weight because it's weightless. So what they do instead is they have like something like a Bowflex. In fact, Bowflex was essentially designed to be used as a zero gravity exercise machine. It's resistance based. It doesn't require weight, doesn't require gravity to work. So they can stress their muscles and bones a little bit more, okay, with resistance based exercises. They also have a treadmill and a bike. Now, the treadmill has like this bungee cord, like it looks like a life preserver with bungee cords on it, okay? And they put it around their waist and cinch it on so that they can hold themselves on the treadmill, right? Because if you try to run on a treadmill in space, you just fly off the treadmill, right? So this thing holds them on the treadmill and they can walk or even jog a little bit. They can't really outright run because they'll get seasick because the thing will just go up and down, okay? But they can walk at least and stress their muscles and bones a little bit. Cardiovascular is also a problem. You got to be able to make your heart and lungs work, okay? And it's not like you can, go for a run around the International Space Station. It's not very big and there's no gravity, so running is not practical, right? So they have these ways that they're trying to overcome these problems. If you don't use your muscles, you don't use your bones, they'll weaken. When they weaken, things start to build up in the blood in higher amounts than they should, especially calcium. If calcium starts to build up in the blood, the kidneys will try to get rid of it. And what will you develop? Kidney stones. Okay. Now, kidney stones on Earth are, they can be problematic. They're painful. Okay. To get rid of one, to pass one is quite a painful experience because they're just like a little jagged rock. Okay. They're just crystallized calcium kind of minerals and stuff. So yeah, they can be quite painful to pass. The issue with passing a kidney stone is not so much that, it could block your urinary tract or something, which sometimes it could if they were really big, but more that it's a jagged rock. And when you're passing it, it'll often cut up your urinary tract, which can lead to infection. Okay? Infection on Earth, not a big deal. You go to the hospital, you get some antibiotics, and you get better, and you're fine. On the International Space Station or on a spaceship traveling to Mars, kind of a big deal. Okay? You don't want to get sick, okay, in a situation where you could be hundreds of millions of miles from the nearest hospital. Okay, that can be a big problem. So, okay, all of these are things they have to be concerned with. Okay, obviously another thing would be higher radiation dose. When you're outside the Earth's magnetosphere, you don't have the protection from all of the sun's nasty like gamma rays and particles and stuff like that. Okay, you also have a change in the distribution of fluid in your body. On Earth, fluid generally moves towards our feet and legs. Okay, so we look like we normally do. You go into space, and for the first couple of days, you are very arthritic, especially in your hands and back, because the fluid that's normally in your legs redistributes everywhere, and you actually look all puffy and swollen. Okay? In fact, the first couple of days, your face might look like you just win a few rounds with a heavyweight boxer. Okay, because you'll actually be that puffy in the face. You sound congested because all of this fluid gets up into your sinuses and stuff like that. It can be quite unpleasant actually for the first few days, okay, while you're there, while everything kind of settles down. Okay, that's kind of the physiological stuff. There's also some sensory things that can be a problem. What do we rely on for balance? Yeah, your balance organs is really in your ears. Okay, in the inside the kind of the middle or inner ear. Okay, there's like the cochlea. Okay, that thing looks like a seashell kind of. Okay, and in there is kind of where some of your balance happens. There's little they look like hairs, but they're not hairs. They're specialized sensing cells that detect which way you're leaning. Okay, on Earth, gravity pulls them downward. So if I lean to one side, okay, they tilt and they tell gravity, or they don't tell gravity. They tell my brain, hey, you're leaning. Make sure you tense the muscles on the other side of the body so you don't fall over. Okay, and that's how we can maintain our balance. Okay, the middle ear tells us which way is up, which way is down, if we're tilted or whatever. In space, that doesn't work at all. Those things just wave all over the place because there's no gravity. So they're constantly screaming at the brain. You're upside down, you're right side up. You're leaning, you're tilting, you're falling, and the brain, it's like that car alarm that's always going off. You eventually just go, oh, the heck with it. I'm gonna try and ignore it. Okay? And the brain will actually just stop listening to the middle ear. Okay? It will not use it as a balance organ anymore. Instead, it'll rely on what? Rely on the eyes. Okay? We almost never use our eyes for balance on Earth. Okay? But in a zero gravity situation, astronauts begin to rely on their eyes for balance, which is fine in zero gravity. It only becomes a problem when they go back to a gravity environment. Okay? Because in a gravity environment, now they're relying on their eyes. If they turn to look, their brain goes, oh crap, we're falling. And it'll do something weird with the muscles, and the person will actually fall. Okay, because it started relying on the eyes to tell them which way is up and down. Okay, in a zero gravity situation, there's no up and down. Okay, the floor and the ceiling are the same thing. Okay, but in a gravity situation, that's a problem. So what they would be worried with is if they sent a crew to Mars, which hopefully is going to happen in our lifetimes, okay, that they'll have been in space for 6 months. Their body will have adapted to zero gravity. They'll come out onto the step ladder or whatever to go down onto Mars, and they'll take a look around, and instead of making the first footprint on Mars, they'll make the first faceplate print on Mars because their brain will get confused and they'll fall. Okay. When they bring people back from the International Space Station, they've been up there for months. Okay. Even when they had the space shuttle, okay, they would always essentially lock arms. They would have crew members from Earth, okay, lock arms with the returning astronauts and walk them down the hallway. Because they found the first couple of times they were bringing people back, they looked foolish, like they actually looked drunk when they came back, because there'd be reporters there, oh, taking pictures, whatever, and they're like looking over at the reporters and they just walk that way, okay? And so they would just fall and look silly, okay? This was another thing that Chris Hadfield was doing research on. He actually, when he came back, part of his return to Earth stuff was he got put in a virtual reality driving game, okay? So he's watching this screen and he drove off the road constantly, because you know what we do, right? We're supposed to turn and look and check mirrors and stuff like that. And every time he turned to look, he drove off the road, right? Because his brain is, oh man, we're going that way, okay? Because his brain still hadn't started listening to the middle ear as a balance organ again. It takes a few days for them to return to that messaging system as opposed to listening to the eyes. Okay? There can be a lot of very acute nausea in the first few days when the brain is still listening to the middle ear, because it's like you're upside down, you're right side up. Oh God, we're gonna get me sick. Okay, and so there's just a lot of stuff, okay, that can be very difficult in the first few days, and that's a big concern. You have to have a stomach of iron to be an astronaut. What happens if you throw up in a spacesuit? You'll die. If you throw up in a spacesuit in zero gravity, where does the puke go? Everywhere. And it's zero gravity. It's not going to fall down to the feet. It's just going to float around, and you're going to inhale it when you breathe in the next time. Can that kill you? Yeah. Aspirating your own vomit can kill you. It's acidic. If it gets into your lungs, it can destroy the lung tissue. That's why people, if they get really intoxicated, can actually choke on their own vomit. Okay, they'll puke and it'll just go right back down. Okay, I've actually seen the guy like it went up and it was like a fountain, whoop, oh, and right back down. Okay, and he inhaled it. We had to turn him over and we had to like beat on his back and get him to cough and then take him to the hospital. Okay, because it can damage your lungs really badly. They have to flush them. Okay, it can be very serious. So yeah, you can't be an astronaut if you get motion sick easily, okay, because it can be fatal in a spacesuit. All right, so all of these are things that can be a real problem. Okay, they're trying to come up with ways to kind of generate artificial gravity. So I'm going to show you here a few videos that Chris Hadfield made while he was on the commander, actually, of the International Space Station. Kind of life in space stuff. How do I deal with zero gravity in this situation? How do I deal with zero gravity in this situation? There's so many weird things about zero gravity, okay, that we just don't even think of. We just take for granted on Earth that we don't have to worry about. Okay, and there can be a lot of problems with other things. For example, when they sleep, you don't need a bed. Okay, I don't know what happened. They used to have a video in that playlist where he was sleeping. Okay, and all you do is you just like wrap yourself in like your space PJs, and then you just like literally go into your little bunk, which is a hole in the floor. Okay, it's like a little. It looks like a shower. Okay, it's like a small shower. You just go in there and fall asleep. You don't need a pillow. Nothing. You just yeah. You got a little, yeah. It's dark, right? A little privacy. Otherwise, the lights of the space station are always on. Someone's always on shift, right? Yeah. But they showed a picture of a guy and he's just okay. His arms just right out, because he's asleep. You don't get a kink in your neck or anything like that because there's no gravity to put any tension on it. All right. So the idea here is that if we want to produce artificial gravity with kind of practical technology and not magic, okay, what we have to do is create at least some part of the ship or station that is a spinning drum. Okay, if we have the spinning drum, then it's just like the gravitron ride at the Stampede. Okay, it spins around, and if you're standing on it, your inertia is that you want to leave the circle, but you're pushed into the circle, and the circle pushes you back towards the center, and so you feel like there's gravity. It's not real gravity, but it makes it feel like there's gravity. Okay. But if you move away from the center of the circle, then you're going to feel less and less gravitational pull, right? Because again, R will get less and less and less. All right, so this is how we would do that. We would have the spinning drum, and then the person standing, okay, right here, right? So they're standing right here. Okay, they want to go this way because that's the way they're going in that circle at that moment. But there's a normal force here. Okay, that's reacting to their inertia, pushing them back towards the center. And it feels just like gravity feels. It's a force against your feet. Right now, if I was to jump, it wouldn't be like jumping on Earth. I jump on Earth, I go straight back down. Okay, I jump here and I like arc. Right, I would arc across because I would have this angular momentum that would carry along with me. Okay, so it'd be hard to to like jump perfectly vertically, right, in a situation like that. Conceivably, if the drum was small enough, you could jump from one side to the other, right? Most of the time, be spinning enough that you wouldn't be able to launch yourself like that. Okay? It would feel, if it was big enough and fast enough, it would feel just like normal gravity. You'd hardly be able to tell the difference. Yep. If it was big enough. If it was a small one, you could easily propel yourself across. Yeah. Okay. Now, the practicality, though, of a small one is that it, like where the bigger it goes, the faster it has to spin. Okay, so there becomes a practical issue with perception. You can see the star field spinning, and that can affect your perception, make you dizzy or sick. But if it was big enough, you would hardly notice. Okay, the real issue comes if you're working on the outside. Now, if you have to do an EVA and you're working on the outside of a spinning object, if you let go, you get thrown off in a straight line. Okay, it works great when you're on the inside of it, but if you have to do any servicing on the outside, you have to shut it off. You have to turn off the rotation. Okay, otherwise, bad stuff will happen. All right, so we would set it up like this. We would want that centripetal force to feel like gravity. Okay, and it would allow us to calculate how fast this thing needs to spin if we knew the radius, which we would know because we're building it. Okay, so if we knew the radius, okay, we could find the speed. What's going to happen to people's mass in this equation, though? Well, if I spun it fast enough, yeah, I could make myself feel heavier. But in this equation, if I do any manipulating, what happens to mass? It cancels off, which makes sense. Everybody in the space station should feel like they feel at home. Okay? If I'm heavier than you, I feel heavier there. than you do because I'm heavier here than you are. Right? So mass would cancel. We would all have, it would affect us all the same way. All right, so anytime you're dealing with artificial gravity, it just sets up like this, Fc equals Fg. Unless they said you want it to feel like half gravity, then you would go half Fg, or twice gravity, then you would go 2Fg, okay, or something like that. All right, I don't know if I have time to show you these other ones where we actually have videos of, like, from movies where they're showing this zero gravity stuff. I might have to show you that tomorrow. But this is a picture of, I don't know if you've seen 2001: A Space Odyssey. That movie's actually older than me, so it's like really, really old. But okay, it was it's based on a book, and it was written, okay, by a guy who actually worked for NASA. So he came up with all these great ideas that NASA basically is still trying to come to fruition, but some of them they have. Okay, artificial gravity is not one of them yet, but you can see this part of the ship is a spinning drum. And if you've seen, The Martian or anything like that, they all have a part of the ship that spins to generate artificial gravity. Don't start packing up, guys. We got 5 minutes left. Okay? The clip's just longer than 5 minutes. Okay, so that's what we would have. Okay, we would have this spinning drum, right? And you can see here that everything obviously in a spinning drum has to be arced, right? So even all the furniture, it can't be flat on the bottom. It's got to fit into that curved surface, okay, which makes design and construction a bit complicated. All right, so I'm just going to delete this here. We want to figure out what speed the inner surface of this space station, which is big, has a radius of 1,700 meters, okay, must move so that the astronaut at point P, right here, okay, experiences a push on their feet that equals their Earth weight. All right, so we just said, if we want them to feel like they're at home, we want to use Fg. What's providing Fg, or is the centripetal force. Okay, so this is m times g, and this is mv squared over r. All right, so I'm looking for V. We already said M is going to cancel. R is going to come over here, and then we're going to square root. So V is going to equal the square root of GER. Okay, and when we plug all this in, okay, V will equal the square root of 9.81 times 1,700 meters. So a really, really big space station. All right, so it would have to spin at 129 meters per second. So it would be almost impossible to service anything on the outside of that, okay, because you would be moving that quick. You'd never feel it on the inside, okay, but on the outside, if you were to let go after having been on it, you would fly off at 130 meters per second, okay, which would be bad. Okay, so obviously there are some issues with that, but on the inside, you'd feel perfectly normal, just like you do on Earth. All right, everyone kind of follow that? I often have an artificial gravity question on the unit exam. Hint, hint. I just told you. Okay.
Once it started spinning, would you disconnect the middle part, and wouldn't it just sit there?
Well, again, disconnecting the middle part would mean that it would be able to move back and forth as well as around and around. Like, it would need to have some connection point. You're right. It would. In space, there'd be no air resistance, but there'd still be a resistance on the pivot, like the rotation point in the middle. So generally, it would be somewhat powered. Okay? And it's probably not a motor that would power it. They would probably have jets that would start the rotation. Okay? And now, obviously, if it's not spinning, you're in zero gravity. As it spins up, you would get more and more gravity. You'd feel heavier and heavier as the spin picks up. Yeah, well, that's essentially what we did here. Okay, I'm just saying in this situation, we're saying this force is being provided by this force, right? Okay. All right, so obviously then we want to feel like we're at home, so that's how fast we have to make it go. Okay, and that's the idea behind some of the science fiction stuff that we've seen. Like Arthur C. Clarke, the guy who wrote 2001: A Space Odyssey, also wrote a series about this big cylindrical ship. Okay, and it basically spun to produce gravity inside. Okay, it would be spinning at a very high rate because it was very big, so probably close to what we were looking at there. Okay, and on the inside of that ship, okay, they would have to have big lights, but they could have fields, they could have lakes, they could have all that kind of stuff. Okay, because there would be gravity there provided by the spinning. Right, everybody follow me there? Like the water wouldn't float away, it would be held there, just like anything else would be held there, okay, because of that artificial gravity. The problem would be if the spin ever stopped. Okay? The spin ever stopped, everything floats away, right? It's all zero gravity then at that point. Okay? In fact, in this ship that he designed, there was what they called the cylindrical sea in the middle. So a body of water across the middle, a full band of water separating one side from the other, right? On one side of it, they had a cliff that was only a little bit, that was only like let's say, 20 meters tall. But the cliff on the other side was like 200 meters. Because when the ship would accelerate, the water would push back, right? So they had to have a tall cliff on one side to keep the ocean from flowing over. Right? No, I don't know.